Okay, so we're going to look back now a little bit. There's a theorem that we've just seen, and it's very similar to a theorem that we saw a long time ago. So we're going to look back, make a comparison there, and draw a nice connection. Okay, so let's see here. We're going to look at these two theorems here. So here's the old one. This is an old theorem from a long time ago, way back at the beginning of the course, right? So that's that business about particular and homogeneous. Um, didn't seem like a particularly useful theorem at the time. It made the observation that if you wanted to understand solutions to a system, that instead of doing a row reduction, you could instead well, do two row reductions, right? One to find a particular solution, and then an entirely different row reduction to find the homogeneous solutions. Why would we ever do this? Okay. Well, we've seen more recently now this theorem. And this theorem is going to be super important and super practical and super useful, specifically if you have this kind of a differential equation that we're now looking at kind of for the first time. And if you want to find its general solution, then you can do that by way of a different sort of approach, namely finding a particular solution, finding homogeneous solutions, right? Um, and adding them. Now, why is this so useful when the previous one wasn't? Well, it just turns out these are different games. There's no such thing as a row reduction for these kinds of questions. And it's going to turn out, as we're going to see, that this equation here is much easier to solve, much easier. Powerful methods of linear algebra that we can use to solve this kind of equation. So that's going to be really nice. And then how do we find the particular solution? Well, it's going to turn out that finding a single solution is something that's actually that we can do. That's something that's actually kind of reasonable. Okay, so it's going to turn out this is a great theorem. Okay, but now let's focus for a second on the similarities. Look how similar this theorem looks to this theorem. In fact, when I wrote these down on the page, I wrote this one first, and then I did a copy paste. Right, I literally copy pasted down to here, and then changed a few things. I had to change that to this, etc. But they're super similar in structure. Very much of an eyebrow raiser, and so reasonable question then: why? Right? How could it be that these two very different questions, right? In one case, we're interested in solving a system of linear equations. And here we're looking at a differential equation, cosmetically very different. How could it be that there are two such powerfully similar theorems about them? And well, not surprisingly, it's because there's some common features to the problem, right? They are different in some important ways, but they're also similar in certain ways. And those similarities are what caused that to happen. So reasonable question to ask, what are these key common features that make the theorems work, that make both of these theorems, you might say, that makes this result work in both cases, right? The fact that these common features allow that make these common features actually pretty interesting. And here they are. In both cases, we're doing vector space operations. All of the algebra that we're looking at, pretty much, whether we're looking in the domain or in the target, it's all vector space operations. And the other one is linearity. In both of these questions, there is a function involved, and in both of these cases, that function is linear. So going back up here to see what we're talking about, here we're looking at, in the domain, we're looking at vectors in Rn. Here, we're looking at vectors in a very different vector space of functions. So yes, different, right? But they have in common that both of these are vectors in a vector space. And likewise, looking at the outputs, that's a vector in Rn. This is a vector in a vector space of functions. They're both in vector spaces. And what we're going to see when we start looking at the proofs is that the algebra that I do in these little worlds are vector space algebra. Okay, and then linearity. This matrix. Recall long ago, we noted that you can think of a matrix as a function and that function has the linearity property. Right? And likewise, this L, right? One of the first observations that we made in studying differential equations is that this is a linear, now we called it an operator. But the idea is that when you put a linear combination into it, then you get the expected corresponding linear combination out of it, right? And we spent some time talking about that in the lecture recordings. Okay, so very different things. This is a matrix. This is a linear differential operator, totally different things, but they have this common feature that they are linear. Okay, so those are those common features. I guess you can say that's cute and all, that we've seen what they have in common. So what can we do with this new knowledge that we've identified what these have in common? And that is we can try to generalize these results. I mean, the fact that these two questions have something in common that makes kind of what I'm going to loosely call the same theorem work in both cases. Well, hey, maybe there's other contexts in which the same theorem will work. And maybe there's a lot of them. And maybe we don't want to keep having to state and prove what morally looks like the same theorem over and over again. Maybe we'd like to do it once and be done with it and have that to use at our convenience and our leisure at any time in the future. So that's what we're going to do. We're going to use, we're going to set up a context where we are looking at vector spaces and a function between them that's linear. And then we're going to try to generalize. Okay, so here we go. Suppose we have a couple of vector spaces, right? And then we have a linear function between them, you know, from V to W. Right. And again, what do I mean by linear? Just a reminder, linearity, recall, means that if you put a linear combination in to the function, then you get that same linear combination out of the function. Okay, and again, this linearity property, we've seen this in several different contexts at this point. The linearity property is always the same in all of these contexts. By the way, we are going to generalize this pretty soon. It'll be a couple of weeks, but we are going to formalize this idea of a linear function so that we don't have to keep saying, well, it's going to be kind of like what we did before. We're going to have a single generalized concept, an abstraction, a new abstraction that is ultimately basically just this. Okay. All right, so here's the generalized theorem as it seems it ought to be stated. Now, we haven't proved this yet, and we are going to, but this would be, I mean, if I look back at these theorems here and see the pattern, right, and I've got a linear function and I've got vector spaces in and out, and it kind of seems like, following the pattern, that this should be true. So, not a matrix necessarily, not a linear differential operator necessarily, but something that has that shared common feature of both of them, this linear function. Likewise, not vectors in Rn necessarily, not certain categories of functions necessarily, but any objects in any space that has vector space operations. Okay, and it sort of seems like we ought to be able to talk about a solution to that equation and call it a particular solution, and that we should be able to talk about the associated homogeneous equation and talk about correspondingly homogeneous solutions. And doesn't it seem like, again, just fingers crossed, kind of noticing the pattern, doesn't it seem like if I take particular plus homogeneous, shouldn't that always give me a solution? And if I have any solution, shouldn't that always be particular plus homogeneous. So that's what we're expecting to be true, hoping to be true, just following the pattern. But now let's actually prove it. And by the way, this question of what we think ought to be true, it is true. And we are now going to prove it. Not only is the theorem familiar, I think you're going to find that the proof will be familiar as well. It's basically the same idea of how to prove it. Look back, by the way, at your convenience at those two old theorems and look at how they're written, how the proofs are written. And what you'll find is that this is really familiar. It looks like a lot of the same ideas because it is. Okay. So if we have, starting off going this way, right? So that means that we are allowed to assume, oops, change colors here. We're allowed to assume this, that we have some vector x that's a solution to that equation. And let's not forget, by the way, that of course we already, and for this whole discussion, we have this thing called a particular solution that is also a solution to this equation. So I have x and I have xp. And so look, I can define this thing called x minus xp, right? That is, I'm going to call this xh. Now, what I need to show is that there is this thing called xh, but for one thing, I need it to satisfy that, which of course it does, but also I need this to be a homogeneous solution. So I need for ax to equal to zero, excuse me, for tx to equal to 0. This is what I need to show at this point to confirm what I need to confirm. Okay, well, so is this a homogeneous solution? Let's see. Well, we need to compute T of H. By the way, I'm not giving away the punchline here. You can see it is going to work. But why does this work? Well, because if XH is X minus XP, plug that in, use the linearity. Linearity means a linear combination in gives a linear combination out. T of X is B. T of XP, whoops, consistent with my pattern, XP is also B. And so we get B minus B, which of course is 0 as required. And so on the assumption that I have a solution, we have now shown that it definitely is the case that there is a homogeneous solution XH that satisfies that formula. So we have successfully showed this. Okay, and now let's go the other way. The other way is a little bit more direct, right? How do I show that? Well, so I get to assume that there is a homogeneous solution XH that satisfies this rule. Right? And I just want to show that T of X is B. I want to show that X is a solution to T of X is equal to B. So I need to compute T of X and I need it to be B. Again, not giving anything away. There it is. You can see this is going to work out. But why does that work out? Well, because we are assuming X is XP plus XH, right? That's what we're assuming for the purposes of this part of the argument. And let's see here, we have linearity that we can use. Again, same sort of linearity. And of course, for all of this discussion, don't forget, we know that XP is a solution. So T of XP is B. And this, we are assuming XH is a homogeneous solution. And so T of XH is equal to 0. And therefore, as required, T of X is B. So this is no longer a question. This is a established fact. And therefore, as we hoped, we have proved that side of the argument. Okay. All righty, so we have proved the result. We have this theorem proved as a generality, not just about matrices and vectors, not just about linear differential operators and differential equations, but about any situation where I have vector spaces and a linear function between them. In any such case, there is a what you might call a particular and homogeneous sort of a theorem. Okay, so why do we care? Right, what's the win for us? Why is this something we should be interested in? Well, so for one thing, this proves both of the original theorems for us, right? So we see now that we kind of wasted some energy previously. We didn't have to prove both of those theorems separately. We can prove them just all at once, right? This one proof proves them both. In the original case, when we were looking at systems of equations, the matrix was our linear function. When we were looking at linear differential equations, it was this linear differential operator that was our function. Yes, they're different, but these both have that linearity property. Back when we were looking at systems, it was Euclidean vector spaces, fine. When we were looking at linear differential equations, it was vector spaces of functions, fine, okay. Different cosmetically, but they both are pairs of vector spaces, and that's ultimately what we saw, all that we really need. We needed to be able to do vector space algebra. In other words, adding and scaling and that sort of thing. Okay. More than that, though, we now have an explicit understanding of what it is that these two theorems have in common, right? Again, so if you go back to here, at the time that we first noticed this, it was an eyebrow raiser, right? Highly suspicious. Something's going on here, right? We could see that there was a connection of some sort. We didn't really have a full understanding of what it was. We now have a very crisp and explicit understanding of what these two theorems have in common. What they have in common is that they are both special cases of this same single theorem, right? They are single special cases of a generalized result. You might say that this is a unification of those two facts. So that's good, right? To have an understanding of something that you previously only had sort of an inkling for. Okay. By the way, more than that, in chapter 6, we're going to see another important example. So another special case. So don't think of this just as a unification of two previous facts and we're done. No, there's another big one coming in chapter 6 that is also just a special case of this theorem. And when we get there, we won't have to prove it. We won't have to prove the theorem again. We've already proved that result in chapter 6. We just don't know it yet, right? Because when we get to it, all we're going to do is we're going to say, well, oh, here we are again. We have a new pair of vector spaces and we have a new linear function. Oh, good news. I already know a theorem. And proof has been done. I don't have to rewrite it. Okay. Lastly, any other time in the future, maybe in this course, maybe not, but point being, in your futures, outside of a linear algebra course, anytime you find yourself looking at a linear function, and the world's full of them, right? Any linear function between any two vector spaces, you've already got a theorem there too, right? So this is consistent with our theme of generalization and abstraction that we talked about. We first talked about this with just talking about vector spaces alone, right? We've proved theorems about vector spaces in the abstract and found that spares us having to prove them again for future situations that we encounter. Same thing here. And that's really the power of abstraction, is it allows us to do something once and never have to do it again, and yet still be able to use it in all future situations that we encounter. So that is very likely to happen. You will encounter things in your futures that are linear, and good news, again, you already have a result here. Okay, so I think this is a really nice connection. A lot of big ideas, powerful ideas in this generalized result, and again, in how this is another example of generalization. Okay.